Hey everyone. So yeah, my doctor's appointment is today at 11, so not gonna make it into school. But I obviously can't waste the day because you know me. And we're gonna talk about today the idea of yesterday we talked about centripetal acceleration. Today we're gonna extend on that a little bit with centripetal force. Remember from yesterday that's the word centripetal. Make it a little thicker. The word centripetal means center-seeking. So it is the center-seeking force that tries to bring something towards the center of a circle. And at its most base thing, really it's the net center-seeking force. There are different situations. We'll do a couple of them as sample problems that will show you how we can get a center-seeking force to go towards our centripetal force. So centripetal force is, we're getting good with our subscripts, it's F sub c, and F sub c is found through a relatively simple equation. It looks very similar to Newton's second law. F sub c, which is centripetal force, equals mass times centripetal acceleration. If you remember from yesterday, there's two ways that we can find centripetal acceleration. First is tangential velocity squared over the radius. The second was omega squared times the radius. So really there's three different equations that we can use to explain or calculate the centripetal force. And the centripetal force is just in its most basic definition, it's the force that tries to push the object, sorry, the pen's a little iffy today, tries to push the object to the center. And this force, I want to stress that it is not a different type of force. The centripetal force itself is not a type of force like the normal force, the tension force, that you can just put in and say that is the centripetal force. Centripetal force is a classification of a force rather than a type. Classification rather than a type. So the tension force, for example, could be the centripetal force. The normal force could be the centripetal force. The force of gravity could be the centripetal force. The forces that we've talked about are the types that you then reapply and rename as the centripetal force depending on what's happening. So let's look, I mean, really that's it. Those are the notes for centripetal force. But they can matter a little bit. Sometimes we want to, depending on how the situation is, whether it's horizontal or vertical, we've got to take into account other forces before we can just determine what our centripetal force is. And the best way to see this is through sample problems. So, get rid of that and bring up a sample problem. Alright, so we have centripetal force of a 1,000 kilogram car going around a 30-meter radius at 20 meters per second. Alright, so just looking at our units, we have a radius of 30 meters, we have a mass of 1,000 kilograms, and meters per second, that's telling you that that is a V, and since we're dealing with circular, it has to be VT, has to be 20 meters per second. So, you look at the notes you just took and realize that centripetal force, at its basic, if you have this type of stuff, is mvt squared over the radius, which is 1,000 times 20 squared over 30. Putting that into your calculator, 1,000 times 20 squared divided by 30. You don't have to do any conversions, and I get a centripetal force of 13,333 repeated. And force has units of newtons. So the centripetal force, the value of the force trying to pull you into the circle of the car rounding the curve. So there's my car. The force, first of all, is acting to the very center of the circle, of the curve. Sorry, this isn't drawn incredibly well. But that's the center of my curve, so the centripetal force and the centripetal acceleration are both pointing to the center of the circle, because centripetal means center seeking. The car is moving with a tangential velocity, vt. And we want to just get an idea of what is causing this force. Centripetal force itself isn't a force. But if you try to think about it, the only thing that could be preventing this car from sliding out and just going out in some direction, well, what could it be? In your car, the only thing, sort of just thinking to myself, the only thing that is going on is your tires are in contact with the ground, so there has to be actually a friction force. So when you're going around a corner, you need kinetic friction to be the source of your centripetal force. Again, that's because there's no tension force, there's no force from your engine, so there's no applied force, there's no one actually pushing you. The only thing that can be acting to the center of the road or the center of the curve is friction. If there's no friction, your car is just going to veer off. Actually, that's not a good drawing. In the same direction as your tangential velocity. You're just going to continue in the straight path through to your inertia. So, in this case, your kinetic friction force is the type of force that is providing your centripetal force. And we found that through just the simple equation. Okay, so hopefully that helps. Get rid of that. If you need to take notes or go back, please do. And we're going to do so a little bit. This down. We're going to do a different problem where we have centripetal force of a 30-kilogram roller coaster cresting a 15-meter radius hill at 10 meters per second. What type of force is this? Okay. So this one, again, similar. We have a roller coaster coming on top of a hill. The hill has a radius of 15 meters. It's at the very top of the hill, so its tangential velocity looks like that, 10 meters per second. And the mass is 30 kilograms. Okay. So there's actually, this is a vertical thing. We have to deal with a couple extra forces. We have to include all of the forces that are acting on this car. Well, just free body diagram. The only two forces that are acting on this car, just in regular, is force of gravity and the normal force. It doesn't say it's speeding up, so there's no horizontal forces. It doesn't say there's friction, so I don't have to worry about that. So there's only two forces. But in order for it to be accelerating and not just flying straight off, there has to be an unbalanced force. And there has to be an unbalanced force down towards the center. So, for that reason, Fg has to win. The force of gravity has to be bigger than the normal force. If the normal force is bigger than the force of gravity, you're going to fly off the track. So, our centripetal force, just from like the previous problem, our centripetal force is mvt squared over r. So 30 times 10 squared, which is 100, divided by 15. 30 times 100 over 15 gives us 200. So our centripetal force is 200 newtons. And the centripetal force is the overall sort of net force acting to the center. Fc is kind of, think of it like the net force to the center. So in that case, our net force to the center would be our normal force minus our force of gravity. Really, we're done the problem up here. But I want to just extend this a little bit because in the worksheet you're going to do, it goes a little bit further. So our centripetal force, which we know to be 200 newtons, has to be equal to our normal force, and our C should be negative because it's heading to the center down, minus our force of gravity. And our force of gravity is the mass of the car times the acceleration due to gravity. So we can set up this equation to try and find the normal force. And again, I'm doing this because in the worksheet that you'll get, or already have, you have a similar type of problem. So we have to find the normal force. So our normal force is 30 Fn minus 30 times 9.8. 30 times 9.8, 294. So you have negative 200 equals normal force minus 294. You want to add 294 to both sides, and you get, just bring it over here, you get a normal force equal to, well, I can do that in my head, positive 94 newtons. First of all, we expect it to be positive because it's up. But what you notice is it's much less than the 294 that you otherwise would feel. And if you think about it, on a roller coaster, when you're going up the top of a hill, for that split second, as you're cresting, you feel a little lighter. Well, this is the reason. You feel a little lighter because your gravity is part taken away, just accelerating you over that hill. It's your centripetal force. It no longer really counts as the gravity force. It becomes the centripetal force. It takes away some of your weight because that weight is required to just pull you around the hill. That's really cool. So that's why you get a little lower. If, for example, you were going down a hill, we'll do these problems. I don't know if we have it yet, but we'll do these problems where if you have a hill that you're going on the bottom of, well, you know this situation. You feel heavier because your gravity's still going down, but your centripetal force has to be up. So your centripetal force and your normal force have to work together to overcome that downward inertia. So your normal force will increase and you'll feel heavier because that's your normal force is what you feel because that's the force acting on you. So hopefully with these you can go through the worksheet number 1 that the sub will pass out, and I will also make a second screencast video just to give a little assistance, but I really would like you to try the worksheet on your own first. So if you could do that, that would be great. And other than that, have a good weekend, and I will see you on Monday. Thank you.